Good morning, dear participants, dear guests. Выключите звук. Не, вот тут. Вот этот.
Включать?
Нет. Thank you for your being here today. My name is Pavlo Trishin. I'm with Olena Kozlova, and we're pleased to welcome you on this conference. Let's begin. We are now continue our section number 1, digital and intelligent manufacturing engineering. And now I'd like to invite Геннадій Аборський, Володимир Голобородько, and Людмила Перпері to present on the topic meteorological aspect of the thermographic study of the turning process. Let me share my screen. I'm so sorry. I'm turn on sound now.
Dear colleagues, allow me to present to you article Meteorological Aspects of the Thermographic Study of Turning Processes, authored by Gennady Oborsky, Volodymyr Koloborodko, and Lyudmila Perpery. Introduction and Major Challenges. The study of thermal conditions in the contact zone between the cutting tool and the surface of a work piece during machining process remains a relevant topic today, as evidenced by the substantial number of studies conducted in this field. As shown by the analysis of literature sources, studies on cutting temperature in various machining methods using infrared thermography are primarily covered in scientific articles in the case study format. As a rule, these publications are focused on studying specific aspects of infrared technology applications, depending on the goals and objectives of the particular research. Unlike contact temperature measurement methods, which are well supported by measurement equipment and are extensively discussed in terms of meteorological issues, temperature measurement methods using infrared technology, which are non-contact methods based on the theory of heat flow and its density. Unfortunately, as of today, lack recommendations for meteorological support and measurement techniques for the field of machining. In this article, the authors make an attempt to define the approach, the application of key terms and their definitions, as well as measurement methodologies and conditions for conducting thermographic studies of cutting processing in mechanical processing. Aim and research tasks. The aim of the thematic study is to investigate the specific aspects of conducting thermographic analysis of the turning processes, to define the sequential stages of the measurement method, and to establish the conditions necessary for their implementation to ensure the acquisition of reliable experimental data. Research tasks define the approach, the application of key terms and their definition, as well as the measurement methodologies and conditions for conducting thermographic studies of cutting processes in mechanical processing. Research methodology. Thermographic investigation of cutting processes in mechanical processing should be understood as research method displays the temperature distribution in the contact zone between the cutting tool and the workpiece being processed. In this work, an infrared camera was used as the measuring instrument for conducting thermographic studies. It detects infrared radiation and creates a thermal image based on the radiative temperature of the surfaces of the workpiece and the cutting tool. It is known that radiation is a function of the object's surface temperature, which allows the camera to calculate and display the corresponding temperature. It should also be noted that the surface emissivity of materials depends on factors such as the surface condition, its color, shape, environmental condition, the temperature of the object itself, and others. Therefore, for thermographic studies, It is essential to first determine the requirements for the conditions under which they will be conducted. Meteorological and technical characteristics of the thermal imager, environmental conditions, distance to the object of study and observation angle, characteristics of the workpiece and cutting materials, and their emissivity. Parameters of the cutting conditions in the mechanical operation. A thermographic study of the turning process was conducted on a universal lathe model 1A616 without the use of cutting fluid or coolant. For the experiments, the measuring instrument used was a FLIR E8 thermal imager. This slide shows the main meteorological and technical characteristics of the thermal imager FLIR E8. A schema of the thermal imager setup relative to the measurement object. The minimum possible distance from the surfaces of the thermal control zone when using this thermal imager model is half of the meter. Considering that various materials will be processing during the experiments, resulting in different types of chips, and to avoid damaging the camera's lens, the distance to the object of study was chosen to be the minimum possible 80 centimeters. The observation angle should be in the range of 45 till 60 degrees. The setup scheme of the thermal imager relative to the measurement object is shown in Figure A. The infrared camera was mounted on a tripod holder, Figure B, in such a way as to cover the control zone, taking into account the necessary camera field of view parameters. Figure C. This slide shows the characteristics of various workpiece material and cutting material pairs and cutting conditions. Result and discussion. During the experimental research stage, it was necessary to take into account and compensate for the effects from several different radiation sources in order to obtain more accurate measurement results. This infrared camera features automatic real-time compensation, but before that predetermined values were input into its built-in software. The emissivity coefficient of the object under study, the visible reflected temperature, the distance between the object and the camera, relative humidity and ambient air temperature. This software is meteorologically significant and is stored in the camera's memory device. Subsequently, after the research, the obtained temperature distribution on the surfaces of the object under study within the zone defined by the camera's optical system's field of view were transferred to a personal computer in the form of thermograms via a USB interface. Results of the experiments. For visualization analysis and processing of the obtained thermograms, as well as for report generations. The standalone software from the thermal imager manufacturer, FLIR Tools, and FLIR Thermal Studio was used installed on a personal computer. As a result of the experimental research, measurement results were obtained under various processing conditions, as described above. This slide shows graphical pictures of the experiments and the obtained thermal images. Results of the experiments. The analysis of the thermograms was carried out using the FLIR tool software by moving the spot meter to the desired area in the digital image of the object under study. It is possible to determine the temperature of the cutting insert, the workpiece, and the chips. In the thermograms, the temperature at the contact point between the tip of the cutting insert and the workpiece is marked as spot 1. The surface temperature of the workpiece is marked as spot 2, and the temperature of the tool's rake face is marked as spot 3. The temperatures on the chip are marked as spot 4 and spot 5. This slide shows processed graphical pictures of the experiments and the obtained thermal images with spots which were described above. Analysis of the presented thermograms. The temperature measurement results are provided in table corresponding to each experimental number listed in tables 3 and 4. To verify the accuracy of the temperatures obtained using the thermal image in the contact zone of the cutting insert tip with the workpiece temperature spot 1. A comparative analysis was conducted with the results obtained through the cutting temperature measurements using the natural thermocouple method, temperature T, during the machining of steels grades C22 and X12 chrome, nickel, titanium. Conclusions. Studies have demonstrated the illustration of the thermographic inspection method for analyzing temperature in the cutting zone during machining processes is an effective approach. It enables research and measurements to be conducted without altering the design of the tool or the workpiece. Moreover, the methods contributes to the rapid and efficient acquisition of substantial data through the analysis of thermal imaging. For example, the measurement data T-spot 1 to T-spot 5 obtained from the thermograms can be utilized to evaluate the temperature distribution across the surfaces of the tool, the workpiece, and the chip. The cutting temperature measurement results obtained through the use of the thermal image were compared with those derived from measurements taken using the natural thermocouple method. The obtained results of the relative error calculation fall within acceptable limits, which confirms the accuracy of the measurement data. For conducting a more detailed analysis of the obtained thermograms, it is advisable to utilize various functions of the toolbar in the FLIR tools software. The study emphasizes the importance of considering meteorological characteristics when considering research using infrared thermography. It should be noted that the chosen observation angle of 55 degrees plus minus 5 degrees within the recommended range increases the actual dimensions of the parameters of the field of view. That means the camera effectively covered a larger area of the cutting zone, as evident from the provided thermograms. At the same time, the accuracy of the camera's focus on the object of study allowed for the clarity of the obtained images. In the regard, it is important for future researchers to correctly set the value of the observation angle when determining the field of view in order to cover the necessary and sufficient area of the cutting zone. Thanks for your attention.
Thank you, Volodymyr. It was very interesting and informative presentation. Now, are there any questions from the audience? Feel free to raise your hand, ask questions. Maybe write your question in the chat. I can show any slide for this question. Okay. Olena.
Good afternoon, Volodymyr. Tell me, please, have you conducted comparative studies with different observation angles to determine the optimal range for other machining operation?
Вимкни микрофон. Turn your microphone.
Sorry. Good morning, dear colleagues. Yes, we had tried different angles of observation, but according of our experiments, we had tried 30 degrees, 70 degrees, 45 degrees, and 55 degrees. According to our experiments, the best result of safety for thermo camera and the best view and the smallest reflection errors we get on angle between 45 and 55 degrees. And just because we have sometimes chips flow away and the best result we got at angle 45 degrees plus minus 5 degrees, because it could change when cutting processes moving during the workpiece.
Thank you.
Okay, I have a question. If the challenges you mentioned with measuring temperature, then machining brass workpiece due to their low emissivity coefficient, that methods would you suggest to improve the accuracy and of thermographic measurements for your materials?
Okay. For metals with highly reflective surfaces, after machining, unfortunately, the most optimal method is to use thermocouples or reference pyrometer for calibration of thermo camera. This is a cause of emissivity of coefficients had to destroy our measurements. Also, I have researched a lot of different information how people try to paint the workpiece or just cover it with any material, but however, any of these methods don't work, because after first try of take of material by tool, you just got again clear surface, and it's again bracing.
Thank you, Volodymyr. Now I would like to invite Микола Ткачук, Олена Зінченко, Андрій Грабовський, Володимир Стіряков, and Anton Saliev Vasilyev, to present on the topic of computational and experiment studies on contact interaction of mock-up samples of complex profiled bodies.
Dear colleagues, we are glad to present to you the result of our research. The theme of the research is computational and experimental studies on contact interaction of mock-up samples of complex profiled bodies. All mechanism meshings and meshing building structure consist of the parts that contact themselves and the other parts from the assembly. Most of these contacts between parts are happening along a complex shaped surface. This complex form is determined by three circumstances. First, there is the need to transmit a mutual motion. This behavior can be described with a complex law within a pair of contacting parts. Therefore, the shape of the contacting parts is formed from the condition of their continuous interaction in mutual moment. At the same time, in the many cases during analysis and synthesis, the shape of the contacting zones and bodies is trying to simplify. That's how the real shape of the contact in the composition of higher kinematic pairs became a point of contact, at least at the beginning, as a geometry of initial contact shape before load will be applied. Secondly, it is a desire to either limit the level of stresses in contacting bodies, or to increase the permissible level of loads that can be transferred between bodies in contact. This in turn can lead either to an increase in the overall dimension of the parts, or to a desire to approximate the shape of their contacting surface. Thirdly, it is a factor of possible disturbance of the nominal synthesized form of the designed parts, and therefore it is necessary to develop research models and methods that take those factors into account, because classical approaches had their own limitation. In addition, the methods of reciprocal calculation and experimental verification of the result accuracy need to be developed. This work is devoted to the solution on the problem on the mock-up samples as example of complex profile bodies contact interaction modeling. A new approach is proposed that combines variational formulation, finite element modeling, boundary element methods, and experimental studies that provide an opportunity to substantiate the parameters of verified models. SIEMS Mechanical was used for finite element analysis tools during research, but other FEA software can be used as well. For boundary element methods and variational formulation implementation was used tools of our own development. For experimental studies, we used 3D printed parts as experimental samples and contact pressure sensitive films for contact pressure distribution patterns registration. Parts was printed using SLA technology with 100% in fill. Contact pressure was indicated by Fujifilm per scale film. For measurement, the contacting elements are placed on a rigid steel stand and loaded with a hydraulic press. Mechanical property of 3D printed sample material was obtained based on cantilever beam deflections. These slides on Figure 6 show 4 different examples of contact impressions. The first two are for cubes with a rigid base. The next two are for the interaction of hemispheres with a cylindrical surface. Similar to cubes and hemispheres, the last result in a pair had an additional intermediate elastic layer. On next two slides on Figures 7 and 8 show geometry and finite element models built for the analysis of the studied body contact interaction. In particular, Figure 7 shows an example of contact pressure distribution during the interaction of cubes with a rigid base. On the right side with an elastic intermediate layer, and on the left without. Figure 8 shows a similar example of contact pressure distribution, but for another contact pair type. The slides show interaction of hemisphere with a cylindrical surface, the right one with additional intermediate elastic layer. In this work, an experimental study of the contact interaction of body was carried out. It was considered two systems in the form of the cube the base and the sphere the cylinder. In parallel with the physical experiment, a number of numerical studies of the same contact interaction were carried out. The result of numerical and experimental studies were compared. Complete and qualitative correspondence of the recorded and calculated result is established. Satisfactory quantitative correspondence of the result obtained by different methods was also confirmed. As a result, the adequacy of the developed mathematical models were confirmed. The parameters of numerical finite element models are also determined, which make it possible to reproduce the feature of the contact interaction of complex-shaped body in the future. In the future, the developed mathematical and software modeling support can be applied to analyze the stress-strain state of contacting complex profile elements of machine building structure. As it can be seen from the above results, the numerically determined and experimentally recorded data on the contact interaction of mock-up samples of complex profiled bodies are in full qualitative and satisfactory quantitative conformity. In particular, the dimension of contact area are determined with an error of 5 to 7%. The level of contact pressure error are at the range of 7 to 10%. In addition, and what is even more important, the trends of changes in the size of the contact area and the level of contact pressure when varying the parameters can see it. Parameters that vary are the diameter d of the sphere, the stiffness c of the intermediate layer, and the pressure force P. Thus, grow d diameter leads to an expansion of the contact area and a decrease in the pressure level. A decrease in C, level of stiffness of intermediate layer, leads to the same effect. And in opposite, with the growth P, pressure force, the contact area and the contact pressure level both increase. In general, it was also established that for a satisfactory description of the contact pressure distribution and the contact area, at least 10 finite elements per width of this area are sufficient. The results of computational and experimental studies of mock-up samples of complex polyhedral bodies testify to the applicability of the developed numerical models for further modeling of stress-strain state of bodies of this type. Thank you.
Thank you, Anton, for an insignificant presentation. Now, are there any questions from the audience? Okay, my questions. Your experiments show a 5 to 7% error in determining the contact area and 7 to 10% error in contact pressure measurements. What factor do you believe contribute most significantly to these discrepancies between numerical and experimental results?
Thank you for the possibility to present and thank you for the question. So we have a couple problems, and one of the most problem is that we need the contact pressure film to register a result because it's additional layer. It has additional stiffness. It's have additional elasticity. They change the result of our contact without the pressure film and with. This is the reason why we add additional elastic layer to understand how presence of the contact film implemented in the result. So we have small for this moment mockups, and that's some problem because we have some difficulties in obtaining the good result from the one experience. We need to create a series of experiments, and then we need to average the result. Maybe those problem came not from the one certain registered experiment, but from our approach to approximate result from the series.
Okay, thank you, Olena.
Anton, hello. You have a very beautiful cat.
It's
Yeah,
your
it's one of character. Unfortunately, we can't add it to the official author list.
Thank
But-
you for
Спрашивайте.
Thank you for your report and presentation. Tell me, please, have you considered extending this research to dynamic loading conditions?
For this moment, no. We want to do that, but we need to make some improvements in first of all our experimental laboratory equipment, and secondly our current variant of boundary element method implementations can solve dynamic cases for this moment. With the finite element method, we can solve it, but we have those two limitations for this moment. It's future. We think it will be in future.
Thank you. Thank you.
Thank you, Anton. Now I like to invite Denis Шульман, Светлана Кружнова, Ольга Омельченко, Natalia Shaleva, and Alexei Omelchenko to present on the topic of reliability assessment of hosting mechanism at fuzzy initial information.
Reliability assessment of hoisting mechanisms at fuzzy initial information. The work of the group of authors on estimation of reliability of hosting mechanisms at fuzzy initial information is offered to your attention. According to statistical data, industrial traumatism and accident rate at hosting facilities has a rather high level. It testifies to necessity of search of effective methods of decrease of accident rate and decrease of reliability of hoisting mechanisms. Objective characteristic of normal functioning under the condition of safety of exploitation of the element of hoisting equipment is reliability. According to the value of reliability, the decision on operation of the element, its strengthening or prohibition of operation is taken. Timely repair, continuation, or termination of operation is determined by the residual resource of the structure. Prediction of residual resource that is estimation of serviceability reserve, is the main indicator determining reliability, as well as the most important element in the system of management of technical condition of lifting cranes and its structural elements in operation. Deviation of values of diagnostic parameters beyond the permissible limits caused by the occurrence of various damages in the elements of the mechanisms serves as the basis for making a decision to carry out the necessary technical actions to restore serviceability. A well-developed reliability theory based on probability theory and mathematical statistics requires complete statistical information about systems and impacts. That is, knowledge of characteristics and distribution laws of all random variables, which is most often absent in practice. The equipment is generally operated for its normal service life, after which inspections, tests, and repairs, if necessary, are organized. However, complete information on certain parameters of the facility is not available. Such information is called incomplete or limited, and uncertainties of this kind are analyzed by methods of possibility theory and fuzzy set theory. On the basis of these theories, it is proposed to consider the problem of forecasting the residual resource when the probabilistic model is difficult to realize within the set problem, and the possibility model provides satisfactory results. Current estimates characterize the degree of operational reliability of the hoisting mechanism at the time of making decisions about its state, and it is reasonable to find them directly on the fuzzy interval. Thus, value 1 indicates a normal condition of the controlled object or parameter, value 0 about its unsatisfactory condition. That is, the closer the value is to 0, the worse the condition of the control object. Consequently, the concept of the current assessment of the operational state does not contradict the concept of the value of the belonging condition of the current parameter of its fuzzy interval. A fuzzy set reveals any object to some category with some degree of belonging. From the point of view of characteristic function, fuzzy sets are a normal generalization of ordinary sets. If we abandon the binary character of this function and assume that it can take any values on the interval 0, 1, in possibility theory the characteristic function is called the belonging function, and its value is the degree of belonging of an element to a fuzzy set. The advantage of the possibilities theory is the simultaneous modeling of fuzziness in the form of a fuzzy set, and quantitative description of uncertainty in the form of a pair of number possibility and necessity. A distinction is made between an upper value of the probability of an event, called the possibility of a no-failure event, and the lower value of the probability of an event, called the necessity of no-failure event. Let us use the consistency condition of the possibility theory in the form of nt is less than or equal to pt, that is less than or equal to rt, where pt failure probability, nt the need for failure-free operation, rt the possibility of failure-free operation. Nt equals pt, the lower value of the probability of failure-free operation, as an indicator of reliability. Rt equals pt, the upper value of failure-free operation. A typical function is taken as a distribution function of the failure probability over the time pi t equals x per negative t minus at in brackets divided by bt squared, where at, bt distribution parameters with t less than at. At denotes the average time to failure. To find the parameters of the distribution, two values of expression 2 at 2 points in time, or two values of the probability of failure obtained by methods of probability theory and mathematical statistics are required. Taking into account production conditions and limited information, it is acceptable to take the probability value as the lower value of the probability of an event obtained by methods of possibility theory. The possibility of an event is characterized by a function. Is the concept of reliability is regarded as a failure. Based on expression 2, we have A equals T max plus T min in brackets divided by 2. B equals T max minus T min in brackets divided by 2 square root of negative in A, where A belongs to 0, 1, risk level which are set depending on the number of known values of the fuzzy variable. Estimation of the distribution parameters is preceded by estimation of reliability, lower probability value, by methods of possibility theory at two moments. P1 t equals 1 minus exp, negative t1 minus a t in brackets divided by bt squared. P2 t equals 1 minus exp negative t2 minus at in brackets divided by bt squared. From 3 we can find at and bt. At equals 1 t minus 2 t2 square root of in 1 minus p1 in brackets divided by in 1 minus p2 in brackets, all this in numerator, and 1 minus square root of in 1 minus p1 in brackets divided in 1 minus p2 in brackets in denominator. And bt equals at minus t1 in numerator and square root of negative in 1 minus p1 in brackets in denominator, or bt equals at minus t2 in numerator and square root of negative in 1 minus p2 in brackets in denominator. Reliability of complex technical systems by the interval of values of the possibility of failure-free operation and necessity of failure-free operation, and the reliability value obtained by methods of probability theory is inside the reliability interval. Let's consider pessimistic estimation of residual resource and optimistic estimation of residual resource. Figure 1 shows the function rt and nt, and the probability curves pt equals nt and pt equals nt plus rt in brackets divided by 2. Figure 1 function rqn and p, n equals 1 minus q, q possibility of failure and the necessity of failure-free operation, p probability of failure-free operation. The place of intersection of the function of the necessity of failure-free operation with a straight line will indicate the limiting time of operation under the pessimistic variant and the time of the last inspection. The intersection of the probability of failure-free operation with the line of the maximum reliability level will indicate the time according to the optimistic option. Now we find the point of intersection of the curve of the need for failure-free operation with the level of ultimate reliability. Using expression 4, we need to find the parameters using the two values of time. Negative bt square root of negative in 1 minus n1 in brackets equals t1 minus at. Negative bt square root of negative in 1 minus n2 in brackets equals t2 minus at. After transformation we obtain in numerator t1 minus at in denominator t2 minus 80 equals to square root of in numerator in 1 minus n1 in brackets in denominator in 1 minus n2 in brackets, where n1 belongs to p1 and 2 belongs to p2. We find at, and knowing at, we find the value of bt. From the evaluation, 1 minus exp negative t minus at in brackets divided by bt squared equal to p norm. We find the value t equals tp. Residual resource under pessimistic option t res p equals tp minus t2. Let's consider the optimistic value. To find the maximum operating time for the optimistic variant, we use the function tp equals 1 minus 0.5 exp negative t minus 80 in brackets divided by bt squared. Then p1 equals 1 minus exp negative t1 minus 80 in brackets divided by bt squared. P2 equals 1 minus exp negative t2 minus 80 in brackets divided by bt squared. Values at and bt we find the same way. Negative bt square root of negative in 1 minus p1 in brackets equals t1 minus 80. Negative bt square root of negative in 1 minus p2 in brackets equals t2 minus 80. Since t1 minus 80 in numerator and t2 minus 80 in denominator equals square root of in 1 minus p1 in brackets in numerator and in 1 minus p2 in denominator. From the equation 1 minus 0.5 exp negative t minus 80 in brackets divided by bt squared equals p norm, we find to. Residual resource under the optimistic function t res o equals to minus t2. The value of the residual resource is within the interval of the residual resource for the pessimistic variant and the residual resource for the optimistic variant. The methodology is repeated for the next lifting crane survey, but the next test time is taken and a new residual source value is determined. As reliability information is accumulated at different points in time, the estimated residual resource will become more adequate. The presented mathematical models based on possibility theory can help specialists in solving problems of optimal determination, prediction, restoration of functional dependencies, recognition, risk assessment of various technical systems.
Thank you, authors. It was very interesting talk. Now, there are any questions from the audience? Okay. I have questions.
Tell me, please, what are the main advantages of the methodology you proposed?
Ольга?
Да. Okay. Okay. Advantage of the use of fuzzy sets in the theory of publicity. Taking into account qualitative information allows to formalize and expect judgments and logistic description which are difficult to resent with numerical values. Uncertainty handling works effectively with fuzzy, incomplete or contradictory information. Decision support provides information on the possible scenarios of a development of a station and the risk associated with them. Or in other words, our fuzzy set-based methodology allows us to determine the necessary estimates and predict the remaining research based on incomplete, fuzzy, or contradictory information, while traditional methods require extensive and reliable information about the object, with almost impossible to achieve. Thank you.
Thank you, Svetlana.
Thank you. My question, how does your methodology account for unexpected deterioration factors that might occur during operation of hosting mechanism, such as environmental influence or unexpected load variations?
In order to integrate the impact of unexpected factors, it is necessary to include fuzzy variables, reflecting this impact in the equation of your result resource model. Thank you.
Thank you, Svetlana. Now we start section number 2, artificial intelligence and digital technologies in engineering. And first presentation, I'd like to invite Vitaly Krivda, Evgen Medvedev, Olga Sakhno, Christian Kornilenko, and Dmitry Mazilov, and to present on the topic new mathematical model to optimize the energy distribution of piston engines in hybrid vehicles. Let me share my screen.
Dear management, guests and conference participants, I will present research results according to the next title: a new neural mathematical model to optimize the energy distribution of piston energies in hybrid vehicles. This research was conducted with co-authors Vitaly Krivda, Olga Sakhno, and Konstantin Kornilenko from Dnipro University of Technology, with Evgen Medvedev from Gdansk University of Technology and Volodymyr Dal East Ukrainian National University, and Dmitry Mazilov from State Biotechnological University. Piston energies are key components of hybrid energy systems used in transportation and energy production. The increasing demand for improved fuel efficiency and reduced emissions requires the development of new models to optimize power distribution among the components of a hybrid system. This study discusses a narrow mathematical model that enables more efficient power distribution between the internal combustion engine and the electric motor to minimize fuel consumption. This slide highlights the significance of the problem. Hybrid electric vehicles and plug-in hybrid electric vehicles significantly reduce fuel consumption and CO2 emissions. For example, Volvo CE hybrid loaders demonstrated a 50% increase in fuel efficiency. However, traditional ECs have limited efficiency between 25 and 40%, leading to the significant heat losses. Optimizing energy distribution between the IC and the electric motor can substantially improve their efficiency. The main objective of the research is designing a narrow mathematical model to optimize fuel consumption and the distribution of the energy flows between the internal combustion engine and the electric motor in hybrid vehicles. The slide demonstrates how the model receives data from the driver, the system controller, and the current vehicle speed. Using this information, the model optimizes fuel consumption and confirmed by the compression graph of the fuel consumption between the traditional system and the proposed model. The green curve shows a reduction in fuel consumption when using narrow mathematical model. This approach will enhance the efficiency of hybrid system through intelligent energy flow management, contributing to increasing fuel efficiency and reduce harmful emissions. This slide introduces the concept of hybrid system that combine an IC and an electric motor, allowing them to operate in optional modes while avoiding inefficient loads. The energy balance model is used for this purpose, where is the power of the IC and is the power of the electric motor. The mathematical model for optimizing fuel consumption by minimizing the loss function, where is the actual fuel consumption and is the optional fuel consumption. This also shows the real-time power distribution adaptation is achieved using a neural network trained on real system operation data. The key input parameters are temperature, load, battery charge level, and total power demand. The research methodology focused on optimizing the operation of hybrid system by minimizing fuel consumption while delivering the necessary power for a research task. First, about energy balance model. The total power is the sum of the internal combustion engine power and the electric motor power. And second is about energy efficiency. The efficiency of traditional piston engine is calculated by evaluating the ratio of useful work to the total energy input, including fuel energy and other losses. About battery energy calculation. The battery's energy state is determined by the considering previous energy levels, energy generated, and energy consumed by the electric motor over a time interval. And finally, about fuel consumption. The fuel consumption is defined as the ratio of the engine power to its efficiency, or equivalently the ratio of electric power to generator efficiency. The objective is to minimize fuel consumption by optimizing the ratio of engine power to efficiency. Additionally, regenerative braking is depicted as a key feature that helps recover energy to recharge the battery, further enhancing system efficiency. Here we can see numerical modeling results showing that the traditional approach leads to fuel losses of up to 50,000 conventional units at the full IC power. The proposed model reduces consumption by 15 and 20% depending on operating conditions. The loss function graph depicting the increased IC power above 60 and 70 kW decreases system efficiency. The optimization of hybrid system operation is achieved using artificial intelligence, which adjusts the power ratio between the IC and the electric motor in real time, based on input parameters: temperature, load, battery charge level. As the key findings, we highlight the following aspects. First, the proposed narrow mathematical model efficiently reduces fuel consumption and optimizes energy distribution in hybrid vehicles. And second, using artificial intelligence enables real-time power distribution adaptation based on operating conditions, opening prospects for further research and real-world implementation of this technology. Further research may focus on enhancing the neural network by employing more complex architecture such as deep neural networks or recurrent neural networks, which will improve the accuracy of predicting optimal energy distribution. My report is over. Thank you for your attention.
Thank you, Olga. Thank you, Evgeny. It was interesting talk. Now, are any questions from the audience? Olena, please.
Thank you, dear authors, for your interesting presentation and report. Tell me, please, have you conducted any real-world testing with Toyota Prius vehicle to validate these theoretical results?
Good day, dear chairs, dear participants. Thank you for your question. We have mentioned that our research is only now on the theoretical stage. That's why no real test on the Toyota Prius have been conducted yet. The 15 and 20% reduction in fuel consumption was obtained through computer modeling, only using computer modeling. But in future, we plan that future experiments are planned to confirm these results. Thank you.
Thank you.
Thank you. And the next question is mine. How does the learning process of your neural network adjust then confirm that with rapidly changing driving conditions, such as switching between urban and highway environments?
Thank you for your question. Thank you. Our study of switching between the city and the highway was not conducted yet, because, as I say previously, it is only now a theoretical stage. But we planning this study is the next step to enhance the adaptation to changing driving conditions.
Thank you,
Thank
Petro.
you. Thank you.
Now I'd like to invite Юлий Гориченко, Анжелика Пархоменко, Карстен Вольф, Олег Поздняков, and Artyom Kulenkov to present on the topic intelligent forecasting for renewable energy system in island mode machine learning approach.
Good afternoon, everybody. I am pleased to present our latest research on forecasting solar power generation in island mode systems using adaptive machine learning methods. This study reflects our ongoing efforts to develop resilient energy forecasting strategies, especially relevant for decentralized and unstable environments. Let's begin with the core problem this work addresses. Here is a quick overview of what I'll be presenting today. We'll start with the problem we aim to solve, followed by the challenges in the current energy systems. Then I'll briefly review related research before diving into the architecture of our proposed forecasting solution. We'll discuss how data was collected, which forecasting methods were explored, and how experiments were set up. After that, I'll present and evaluate the results and finish with conclusions, references, and time for your questions. During wartime, Ukraine's power grid often suffers sudden and severe damage. In such conditions, centralized energy systems become unstable and unreliable. Our goal is to restore power supply quickly by relying on decentralized energy sources. But to make them truly effective, we need precise real-time forecasts, because each energy demand and weather conditions that can change rapidly. That's the core challenge this paper addresses: how to forecast local power generation accurately and autonomously even during emergencies. Traditional energy systems were never designed for war conditions. They rely on central infrastructure, large power plants, transmission lines, transformers, and all which can be damaged without warning either by natural events or enemy attacks. Once damaged, repairs take time. This means cities, villages, or even critical infrastructure might be left without power for hours or even days. To adapt, we need a system that can function even when isolated, and that starts with understanding these vulnerabilities. Let's take a brief look at the existing research on this field. The literature confirms that machine learning and hybrid approaches play a crucial role in the stability and efficiency of modern renewable systems. Our research builds on these foundations by comparing several machine learning strategies under clustered, group, and tree-based experimental setups, aiming to find the best match for real-world island mode systems. To solve the problem, we propose a decentralized forecasting architecture. Each energy node, whether a home, shelter, or medical post, has its own mini-forecast unit. It collects real-time data from local sensors and predicts power generation for next hours. This makes the system independent from a central controller that allows fast, autonomous recovery even if part of the grid is destroyed. The key innovation is embedding intelligence right at the edge, at the local energy source. For reliable forecasting, we need accurate, up-to-date information, and online weather APIs are simply not precise enough in local wartime conditions. That's why we deploy real-time sensors for wind, solar, and battery metrics directly at the site. These sensors connect to a microcontroller that processes and stores the data locally. This setup allows us to react quickly to challenges in the environment and forecast power generation more precisely, even when disconnected from the internet. Our forecasting strategy is based on 3 groups of experiments, each designed to analyze different learning methods and data structures. First, we applied cluster regression approximation using k-means to partition data and then training separate models: linear regression, MLP, and long short-term memory for each cluster. Second, we evaluated group argument accounting, where we built models for 3 distinct feature sets: temporal, historical, and environmental. Models like random forest, long short-term memory, and polynomial deep neural network were trained and then combined. Finally, we addressed tree-based methods like decision trees and random forest, tuning them for optimal performance. This multi-angel approach allowed us to compare not only models but also how they interact with the different data types and structures. Our experiments used data from 2 solar power plants in India, recorded over 34 days. We used a rich feature set, including not just raw sensor values like radiation and temperature, but also temporal features, interaction terms, and rolling metrics. After cleaning and normalization, we trained and tested our models on over 115,000 data rows, ensuring that the setup closely reflects real-world, time-dependent solar generation scenarios. To evaluate the forecasting accuracy, we used different metrics. In the cluster regression experiments, long short-term memory achieved the best accuracy for two clusters, especially for tasks involving sequential data. MLP provided a good trade-off between accuracy and computational cost at 4 clusters. In the group argument accounting methods, The polynomial deep neural network model stood out with the highest overall accuracy. The determination coefficient of 0.61 and root mean square error of 216.44, highlighting its strength in modeling complex feature interactions. Finally, in the tree-based experiments, random forest outperformed decision trees with a determination coefficient of 0.5 and the lowest mean absolute error of 122.51, showing good robustness. These results confirm that the best model depends on both the data structure and the forecasting goal. To wrap up the evaluation, we compared 4 forecasting models under various scenarios. Polynomial deep neural network provided the most precise results when working with the group features, while random forest showed strong generation and efficiency, making it ideal for unstable real-world environments. Long short-term memory also stood out in the cluster-based approach for its ability to capture sequential patterns. These results underline the need to align forecasting strategies with both data structure and operational constraints. In this work, we developed and analyzed a set of experimental strategies for solar power forecasting in island mode systems. The scientific novelty lies in the structured comparison of clustered group and tree-based model strategies, all designed to match real-world renewable energy sources challenges. In the practical side, our models support intelligent energy management in autonomous and disconnected systems. As future work, we plan to extend forecasting to longer time horizons, test leaf-edge deployments, and explore combined predictions control systems for real-time operation. These are the core references we relied on to develop and validate our research. And that's all for now. Thank you for your attention.
Thank you. It was interesting and informative talk. Now, are there any questions from the audience? Okay, Alina, please.
So yeah, if there is no question, so let me ask. So have you considered cases of erroneous forecasting by the proposed method? And if yes, so what measures should be taken in such a case? And one more additional question. So can there be different types of errors and different consequences for the power system? So questions in one, sorry.
Angelica.
So who will answer
Just
the
a
question?
moment.
Okay.
It seems to me Yuli is here.
Should I repeat the question? Or
Yes, please, because it seems to me Yuli is unmuted or maybe something wrong with his
Okay,
computer.
so the question is, so have you considered cases of erroneous forecasting by the proposed method?
Yes, we try to consider several problems, and for now our research is ongoing, and we try to solve several questions connected with these possible errors. But
speaking about this other methods, so what measures should be taken in such a case?
Sorry,
measures?
Yuli. Sorry, Yuli want to answer, and it seems to me he tried to connect. I want to comment about the possible problems with information from sensors that can be used for our system. during the loss of internet connection, for example, information from sensors cannot be fed directly to the decision-making system. So in our system, sensors are not directly connected to the internet. They locally store data in a local base. It was showed on one of the slides. If the connection is lost, the database is not replenished, and then the decision making for forecasting system will simply be based on previous data without evaluation or constant learning of data sets for decision making, and so this will not be a problem.
Okay, thank you very much for your answer. And one more question from organized community.
Okay, my question. If we consider information from IoT sensor in a decision-making or forecasting system, what will happen if the internet connection to the sensor is lost?
Yes, I tried to answer this question previously because it's one of the possible problem, and as we used our database to which the information is stored previously, so it is not a problem. We can use previous information for our decision-making system. So the loss of internet connection is not a problem for us.
Thank you, Angelica. Now, I would like to invite Mikhailo Polyakov, Andrei Pirozhok, Anton Ryabenko, and Alexei Polyakov to present on the topic of methods for reducing the dimension and expanding the functionality of control automata of systems.
I am Mikhailo Polyakov. Together with my colleagues from the National University Zaporizhzhia Polytechnic, present the report Methods for Reducing the Dimension and Expanding the Functionality of Control Automation of Systems. In slide 2. FSM is a model of control automata. Classical FSMs are described by a tuple 1, where X is the set of input, Y is the set of output, S is the set of state, S0 is the initial state, mu is the output function, delta is the transaction function. The automation are widely used in the practice of designing control systems. The slide shows a description of a traffic light machine as an example. Let us note a number of properties of real control systems, the formalization of which within the framework of the tuple 1 is impossible or leads to a significant increase in the dimension of the control automata. These properties are shown on the slide. The purpose of the work is reducing the dimension of control automata by expanding their functionality. The objective of the work is to modernize the system control structure and display new functionality in the FSM tuple. The main properties of the elements of the tuple of classical control machine are as follows. Property 1, the elements of sets of automata are elements of the binary data type. Property 2, the time interval of output activity coincides with the interval of state activity. Property 3. The functions of the outputs mu and transaction delta of the machine are defined in the tuple of the machine and do not change during its operation. Property 4. At each moment of the machine's operation, one and only one state is the activity. The main properties of the operation machines of control unit of the system are as following. Property 6. In the control unit, the input x sub I of the SA machine is considered as an event. Event processing consists of changing of active state, the expression of the truth of which determines the event does not change during the operation of the machine. Property 7. The control action has no gradation. The logic of converting the output into a control action does not change during the operation. Property 8. At any given time, only one event can be active, and there may be no active events. Methods for extending the properties of control machines as follow. Method 1, non-binary. The elements of set of the machine become non-binary, that is, they have more than two values. For example, passive, preparatory, active. You can specify a spot activity, bind the output parameters to the activity level of the state. For example, the output in the active and preparatory states can differ. Method 2, qualifiers. The step qualifier describes the time interval of the output activity relative to the state activity interval. For example, the state of set, duration, and the end of condition, and then the condition of the output activity. Method 3. Nesting. The method consists of interpreting the output of the A1 machine as an action to call the A2 machine embedded in the state. In this case, the embedded machine is subordinated to the original machine and a hierarchy of subordination arises, which can have several levels. Method 4, controllability. This type of control can be implemented in an integrated system. Almost all elements of type of control automata, input operation automata, and output operation automata machine can act as a control objects. Compare the classical and proposed form of FSM, where the set X, Y, S have the same names as in the tuple 1, but the elements of these sets can have both binary and not binary values. C as a set of controls, S0 is the initial state, and the C0 is the initial control. In the set Y, we distinguish four subsets. First, output actions on control object. Second, output executing a call of the automation embedded in the state. 3, outputs for operation automata of a given level. And 4, outputs for the automata on the lower level. A fragment of control device diagram based on binary and n-ary events in the finite state machine is shown on slide 10. As can be seen in the later case, the number of arcs and states in this fragment is reduced by a factor of n. The classic traffic lights control block diagram, and the diagram using output qualifiers are shown on slide 11. In the latter case, the number of states is held. On slide is shown FSM-A2 for traffic light control, in which in state FSM-A2 embedded FSM-A1. The method of embedding automata into a state will allow to reduce the size of the main automaton with repeated use of the sub-automaton. An example of reducing the dimensionality of the machine using the controllability method is shown on slide 13. With the use of the controllability method for managing cycles in the FSM, the number of verses in the graph of the machine decreased by 22% and Rs 33%. Conclusions. It is shown that the graphical representation of the functionality of systems using the classical FSM has a large dimension. This complicates understanding and complicates the design of systems. The known methods of expanding the basic properties of classical FSM tuple elements and reducing the dimensionality of the description of control devices on this basis were systemized and new methods were described. Their methods use the non-binary nature of FSM set elements, FSM output qualifiers, FSM nestling in states, control of the structure and parameters of control device elements of the given and lower levels of the control system. For considered methods, the reducing the dimensionality and expanding the functionality of control automata of system, set theoretical models of these automata are proposed. The effectiveness of the proposed methods is shown by examples of graphical description of fragments of the control units. Thank you for your attention.
Thank you, Mikhailo. There are any questions from the audience? Alina, please, your question.
The first question is, what are the evaluation criteria for the effectiveness of the proposed methods compared to classical FSMs? So is there, what are the evaluation criteria?
I will divide the questions into two. First, what are the criteria of evaluation, the effectiveness? And second, how much more effective are the proposed methods? Answer for the first question. The criteria of effectiveness is the number of vertices and or arcs in the graph of automation. The method is considered effective if the number of the vertices or arcs in graphical model is reduced. And the answer for second question, in the examples given, the number of vertices is reduced by 2 times if you use binary FSM and by n times if you reduce non-binary FSM.
Okay, another one question.
My second question, what potential limitation or challenges might arise then, particularly implementing the proposed extended set theoretical models of control automata, especially in complex hierarchical systems.
The hierarchy of controls is based on pyramid of knowledge forms such as data, information, knowledge, understanding, and wisdom. And also on the hierarchy of activities. Activities are presented at the level of goals, scenarios, machines, and operation. At the same time, one element, for example, an operation, can participate in several scenarios. This can potentially lead to a conflict. To eliminate conflicts, it's advisable to use a priority system.
Thank you, Mikhailo. Now we are taking a break. It's time for lunch, and we will resume at 1 p.m. See you, all participants, in 1 p.m.